My name is Jeff Bier. I'm founder of the Embedded Vision Alliance. The Embedded Vision Alliance organizes the Embedded Vision Summit Conference, which this workshop is part of. I know some of you were at the conference earlier this week. I'm also president of BDTI, which is an engineering consulting firm. For just maybe 10 minutes, I want to take you away from the coding details that you've been immersed in and focus on the bigger picture, because you are part of something big. And I think if you understand that, that can be valuable in informing your work. How many here are currently developing a vision-based product? And of the rest of you, how many expect to be doing so in the near future? Okay, so that's sort of 2/3, 3/4. That's great. The rest of you presumably just needed a day away from the office. That's fine. But those in the first two groups, you're in the forefront of an enormous wave, the era of machines that see. Computer vision has been around for decades, of course, mainly as a research topic. Not much commercial application. Starting in the 90s, it started to become important for factory automation applications, often referred to as machine vision, and it's very important today for those factory manufacturing applications. But still, through the 90s, the 2000s, up until very recently, computer vision didn't really impact our daily lives directly. We didn't tend to interact with computer vision-enabled products very much. Suddenly now that is changing very fast. And there are a number of factors behind that, but the key factor has to do with processors. Come back to that in a minute. The processors are what enables us to proliferate vision across a vast range of products, including cost and power sensitive products. There still remains the question of why. Why bother doing this? And the why is that vision, very much in the way that vision does so much for people, right? Think of all the things that your vision enables you to do, from navigating through three-dimensional space, complex spaces safely, whether you're walking, driving, or on a hoverboard, doing very fine manipulations of objects like threading a needle, reading someone's face. What kind of mood are you in? Are you paying attention? Vision is very multifaceted for people, and it turns out it's also very multifaceted for machines. If you think about it, machines are useful mainly to the extent to which they interact with the physical world, because that's where we live, right? If you're making something that doesn't interact with the physical world, well, maybe it's a cloud application reconciling bank statements or something. That's still useful. But ultimately, that comes down to the money in your hand. Anyway, interaction with the physical world is what makes most machines useful. Cars, microwave ovens, mobile phones, which enable us to interact with friends and family at a distance. And if you think about it a little further, if devices are valuable mainly in the ways in which they interact with the physical world, then the more they know about the physical world, the more valuable they can be. And vision is the most powerful way for machines to know about the physical world. Just as it is for humans, vision for machines enables them to know an enormous amount about what's going on around them, which can enable them to be safer, more autonomous, more personalized and secure, and just more intelligent and capable. I have two quick examples I'm going to share with you here. I'm sure everyone knows that by now that most automakers are shipping vision-based safety systems today for things like automatic braking, or at least passive warning systems to avoid forward collisions. Mercedes has been a leader in this. They've been shipping that kind of capability for several years in high-end cars. What they've done here is take it a step further, taking the same basic hardware and adding new algorithms to add a whole new capability. And this shows the idea of kind of software-defined sensor. You have an image sensor and a processor. It can do lots of different things depending on what algorithms you run, much as human vision can do lots of different things. So check this out. This is a called Magic Body Control feature. And the way it works is the stereo cameras behind the windshield, that are looking out for other cars and pedestrians now are also mapping the topography of the road surface to about 1 millimeter resolution. That information is then used to control the active suspension. Normally, the active suspension waits for a mechanical input, waits till it feels something to respond. Now it doesn't have to wait for the mechanical input. It anticipates the mechanical input from a pothole or an expansion joint or a speed bump. And as you see in this video, the result is that the vertical body displacements that you normally get when going over these discontinuities in the roadway are virtually eliminated. So it's a comfort feature, but it's also a safety feature, right? Because when you hit these discontinuities at speed, you lose traction normally. You don't have as good a grip on the road. The vehicle becomes harder to control. So by improving that, by knowing what's coming up on the road surface, they improve safety as well as comfort. And I think this helps to illustrate the versatility of vision, which if you think about it, I don't believe there's any other type of sensor that can do the range of things that vision sensors and processors can do. One more example, this is the DJI Phantom 4 drone. So this is basically a flying video camera. But in this case, it will automatically follow you, so you don't need somebody piloting it, and it'll keep you in the camera's field of view. So you can be doing your activity, your snowboarding or tightrope walking or whatever, and the drone will follow you. Of course, the next issue is if it's following you but then running into a tree, that's no good. It's a $1,500 drone. So it's got to be able to detect and avoid obstacles. And this DJI Phantom 4 drone, which just recently went on sale, does both of these things. It'll track you and it'll avoid obstacles. You can tell it also just fly from here to here, and it'll do that, but it'll avoid obstacles. And this helps, I think, to illustrate this concept of autonomy, right? Autonomous things need to know what's going on around them. There are various ways they can do that, but vision is the most versatile way to understand not only that there's something there, but what is it? And where's it going? Coming back to what's enabling us to do this now, this is, of course, processors, better processors, because these applications, these algorithms, as you know, are extraordinarily computationally demanding. When we're running complex algorithms on video data, high data rate times lots of computation per data element means lots of performance. The math is simple. If you need lots of performance, but you need it at low cost and low power so that it can go into something like a consumer drone, the way we do that, the way it's been proven time and again by the semiconductor industry that that's done best is with heterogeneous processors. Ideally, the heterogeneous processor gives you the best of both worlds, right? The bulk of your code runs on the CPU, which has excellent software development tools, good compatibility and portability, but the bulk of your cycles, bulk of your compute runs on a more specialized, more parallel processor that gives you much better performance per dollar and performance per watt compared to the CPU. And that's what this little graph here is showing. But of course, there's no free lunch, and the cost associated with heterogeneous processors has been increased programming complexity. They're just more complex. Now you have two separate instruction set architectures with, generally speaking, separate tool chains, and you have to figure out how to partition the workload. It may be a complex and dynamic workload between those two separate processors, or perhaps there are more, or the two may be multi-core CPU, multi-core DSP or GPU, for example. So that's been kind of the rub. We have the processors, but they're tricky to program. And of course, this is where OpenVX comes in, and this is why I'm really excited about OpenVX, because the promise of OpenVX is access that performance efficiency of heterogeneous processors without having to worry about all of the minute details of the underlying processing engines and the coordination of workload and activity between them. Ultimately, I think this is where we have to go, because we have to enable lots of developers to get algorithms running efficiently on these kinds of chips, to enable the thousands of products that can benefit from having visual intelligence. So I think OpenVX is a huge step in the right direction, and ultimately the heterogeneity of these underlying processors is going to wind up being hidden by OpenVX and other high-level abstractions. To wrap up, my view is embedded vision is going to become ubiquitous. I believe it's going to become ultimately, let's say in 10 years or so, economically as important as wireless is today, because it has comparable value and range of applicability. It's going to become ubiquitous. It's going to become invisible in the sense that we don't think about buying a wireless radio these days as an end product. We buy a thermostat or a car or a tablet that happens to have wireless connectivity that accomplishes various functions, but that connectivity is subsumed into the larger product. Similarly, when the Mercedes stops itself to avoid an accident, we don't think, oh, there's a computer vision product there. Well, we do, but the typical consumer just says, whoa, thank goodness my car was smart enough to avoid that mishap. In the process of proliferating and adding value, improving safety, autonomy, efficiency, intelligence, there's going to be enormous economic value created. There's going to be huge business opportunities here for semiconductor companies, for system companies, for services companies. Often people say, well, can't all this be done in the cloud? Why do we need to bother with these sort of specialized, cranky, embedded processors? Can't we just call Google and Microsoft APIs in the cloud? Well, sometimes yes. It depends on the application. Clearly, if the decision is the car going to stop itself, we really don't want to be consulting the cloud. Similarly, the drone that's tracking you, super low latency, high reliability, it's not going to be radioing the mothership to decide, is that a tree or just some glare off a distant lake. It needs to be fully autonomous. So some cases will be fully embedded or edge-based intelligence, some will be fully cloud-based, and many will use both, as, for example, the Google Translate does today. You get a quick read. Sorry, Google Speech Recognition does today, right? You can use it completely severed from the cloud, and it works okay. If it has access to the cloud, it works even better. Heterogeneous processors are today virtually universal. I mean, I see hundreds of embedded vision projects each year, and almost none of them, virtually none of them, are simply running on a CPU, because you need a lot of compute power, and you're constrained in cost and power consumption in any real product. The way we meet that trade-off, or the way we optimize that trade-off, is with heterogeneous processors. Fortunately, with the emergence of OpenVX and other abstractions, we can kind of cheat that free lunch, no free lunch that I said earlier, get the benefits of heterogeneous processors without having to get bogged down in the details of programming them. So this is why I say I think you all are on the forefront of a huge wave. In 10 years, today you could go through a day in your life and not interact with any vision-enabled product at all. In 10 years, you won't be able to do that. Everything's going to be vision-enabled, just the way everything is wirelessly enabled today. And by mastering these kinds of abstractions and tools like OpenVX, you all are on the forefront of making that happen. Since you're working in embedded vision, you should know about the Embedded Vision Alliance. If you attended the summit this week, you already do. If you didn't attend the summit, come visit our website. It's embedded-vision.com. There are tons of practical, technical, educational resources there for engineers, all free. Video tutorials, code examples, demonstrations, etc. Hundreds of hours of video, thousands and thousands of articles. Please check it out, and if there's something that you need that isn't there, leave us a note in the discussion forums, and we'll do our best to fill the gap. On behalf of the 60 roughly member companies of the Embedded Vision Alliance, I really appreciate the opportunity to come here and talk with you. Thank you very much. Do I have time for questions? Yeah? Any questions? Yes?
So you mentioned about heterogeneous compute, and unless OpenVX is adopted by the major OS vendors, how will you have
Yeah, so that's a very good question. Like OpenVX is just a theory unless, I would say it's really the silicon vendors who have to step up and enable it on their chips. And the good news is that's happening. If you were at the expo, the exhibits of the technology showcase at the Embedded Vision Summit yesterday, processor vendor after processor vendor after processor vendor is bragging about their OpenVX support. So most, if not all, seem to be on board, which is very encouraging. And let's be realistic. It takes a while for these things to catch on and to mature, really be industrial strength. And even then, they're not going to be the be-all and end-all for every single application. There's always going to be advanced applications that are really pushing the envelope where maybe you can do most of it in OpenVX, but you need to do some specialized stuff outside. Maybe you need to create your own nodes or whatnot. So I don't want to overstate the case. It's not like we're done now that we have OpenVX 1.0 or 1.1. But what I'm really saying is this is a direction things need to go in. And you all are being here is, I think, being on board with the way things need to go and will go.
But the three major vendors, Apple, Google, Microsoft, OS vendors, for any heterogeneous to be successful, you need their adoption, right? And they're doing their own stuff.
Well, that presumes that all you care about is things like mobile phones and PCs and tablets. I don't care very much about those things. I care much more about my car, my thermostat, my refrigerator, my drone. Those things aren't, running iOS or Windows, right? They're generally going to run Linux. So you make a good point, right? If Apple decides Apple's not going to enable OpenVX on iOS, then that's too bad, right? But to me, that's a tiny, tiny slice of what matters. That's a handful of devices out of thousands that are vision enabled. Any other questions? All right, thank you very much for having me.